This is Math 261. This is section 12.1 on vector valued functions, and this is part 8 and page 8. In this example, we have a vector valued function given to us. R of t equals the cosine of pi t I plus the sine of pi t j plus t squared k. We have t running from negative to positive 1. We're supposed to identify the graph. So we can use the tools that we talked about in the helix example that we did previously in the notes. Part 4, I think it was part 4. Here's our function, and one of the tools that we used was the projection. And in that example, the previous example, we had tk at the end. It's t squared k now, but still we'd want to project onto the xy axis, just like we did in that previous example. So here's our projection. I've also switched over to component form of the vector. This is entirely optional. I find working with graphs, a lot of times it's a little bit easier to see and think about and work with component form instead of IJK form. Both forms have their place for sure, and I feel free to switch between them depending on the circumstance. So to emphasize how the projection works is one reason why I switched over to this form. How the projection works is that the z-coordinate now, for the time being, when we look at the projection, we're going to say forget about it. Forget about z. Make it 0. Okay? And then we have a very similar situation to what we had with the helix that we looked at. We have an x value and a y value, such that when we look at x squared plus y squared, we're going to get 1, because we have a cosine squared of pi t plus the sine squared of pi t, while the cosine squared of theta plus the sine squared of theta is equal to 1. So the projection, the points on the projection satisfy this equation. So the projection is a circle of radius 1 in the xy plane. And projections can be your friend here when you're trying to identify graphs like this. Because based just on that, knowing that, and given these 4 graphs, we can process of elimination it to get it. All right. One thing I want to mention about these graphs, the graph that we're looking at, the actual graph, is a trace, a path, a particle's motion in 3 dimensions. They're using the shading and kind of putting in the surfaces to help us see it. Like if they just drew, here's the path that's being traced out. Let me take any one of them really. This one here. So there's a path like that. But you could see without the blue shading, you'd never see that it was you'd never be able to see that it's intended to be a little offset from the y-axis. You see how that is? So for features like that, or for this one here, if this was all that was given to us, which is the actual graph in 3D, it would be hard to visualize how that relates to much of anything at all. And similarly here, this one, the path comes out like this. But by giving us this shading and stuff, we can visually see it's kind of curving towards us as x increases. It's coming towards us in that case. So that's the type of reason why they're presenting these graphs to us like this, so we can visualize what's going on in 3D. But the actual graph is the path. That's the type of graph that we're drawing now. We're not doing surfaces in this particular section. We're doing the trace it out type of path graphs, a particle in motion. Okay. Now that's important, but what's the answer to the question? There's only one that projects onto a circle in the xy plane, right? So really we can, based on the projection we just calculated, we can conclude it's this one. And, the t squared that we neglected is where the z coordinate is going to come from, and you can see that they're positive z's, or non-negative at least, which makes sense because t is squared. Okay, so as t goes from negative to positive 1, t squared will be 0 or bigger, which is true for all the z values on this graph.